Hello and welcome to another lecture for my class, PSYC 440/640. The class is called Experimental Methods, but is really more of a class on univariate data analytic techniques from a model comparisons perspective. And as I often do, I'm starting with a webcomic. Here you can see it's from phdcomics.com, a great series that you should absolutely follow. And this is one of my favorite comics because it sort of pokes fun at judgments about significant results versus non-significant results and kind of how those make us feel as researchers. You could probably almost read this comic as a slightly deeper critique of optional stopping rules for data collection, which have been implicated as a technique for p-hacking your results. But for the time being, I'll stop interpretation. And I'll move on to give you the title of my talk today, which is obviously more about simple regressions. Not the most inspiring topic for a lecture, or title for a lecture, but hopefully one that gives you a sense of what I'm going to talk about and gets you set up for what I think will be kind of an interesting talk. And hopefully we'll kind of continue and deepen the discussion of some of the topics I brought up last time. Now, before we get into things too much, I'll do a little bit of a review, and this is kind of a general point that I've touched on a little bit before. When we do statistics kind of from the perspective that I take in this class, the model comparisons perspective, we spend a lot of time computing sums of squares. And there are lots of different types of sums of squares. It can be a little bit confusing because it can sometimes be easy to get the names mixed up. You know, sum of squares for compact model, sum of squares for augmented model, so on and so on. It takes a bit of practice, I think, to get comfortable remembering what all these different sums of squares are referring to. As a general point, you can keep in mind that they're all referring to different amounts of error or different amounts of variability, which is almost always variance, associated with either a compact model, with an augmented model, or with the difference between using the compact model or the augmented model on your data set. So it can be a little bit confusing just remembering what these sums of squares are. Take some time and practice it, pay attention to the lecture, and hopefully, if not now, then soon, you'll have it down pretty well. What can also be confusing, and sometimes very confusing, is when different names are given to the same sum of squares calculation. And this, these different names have their origins in different textbooks or in different research traditions or in different contexts of statistics. But it can be confusing when essentially the same calculation is notated differently in different textbooks or in different lectures or in different classes you might take. So for example here, in most of my lectures up to this point, I've used a non-subscripted notation. So if I'm talking about the sum of squares error for the compact model, I'll call it SSE parenthetical C, or just SSC sometimes for the sum of squares for the compact model. In the textbook, that is Andy Field's Discovering Statistics Using SPSS, he usually uses a subscripted notation, SS sub T. Here, or if you look in SPSS in the output, at least the output from the regression module, which we started playing around with last time, you'll see a name total applied, or a label of total given to that same calculation. So all three of those, SSE, C, SS sub T, and total, are all referring to the error in the compact model, the error in model C, or the total amount of error to be reduced. So this is different textbooks, different contexts, same calculation, different names. And you can see some other examples here, like the sum of squares error for the augmented model or the sum of squares error reduced. It's again, this can be a little bit confusing. I know when I first started learning about statistics, I would be sort of flipping back and forth between different textbooks, or nowadays it's more like clicking around on different websites on the internet. I would sometimes get confused and even frankly frustrated by seeing these differences in notation. I'd argue that it's worth learning these different names for these sums of squares, or becoming familiar with the idea that the sum of squares for the compact model is sometimes called sum of squares sub T or total sum of squares, just because then as you move through this class and through other classes and look at different textbooks, you can more easily flip back and forth between the two. But like I did on just the slide prior, I'll try to highlight which notation system I'm using, or I'll try to include reminders in my lecture lectures so that you always remember, or can always focus on, what exactly am I talking about when I'm saying sum of squares error C? Oh, that's sum of squares error for the compact model. That's the total amount of error that we're trying to reduce, or variability that we're trying to explain. Ah, I got it. And hopefully that'll make sense to you, and as we proceed, you'll be less and less confused instead of more and more confused. So with that little review out of the way, here's a bit of an overview for what we're going to cover in this lecture. Basically, I'm going to work through an example to help you test and practice your understanding of working with simple regression. And I'm also going to try and teach a couple new tricks. One of them is centering predictor variables, and the other is using some basic regression diagnostics which are available to you in SPSS and indeed in many other stats programs that you might choose to use. Okay, so imagine that you're a health psychologist who's studying stress, and you're doing a non-experimental study where you have a predictor variable which is heart rate measured at some baseline period, and we're operationalizing heart rate as just beats per minute. And you've got an outcome variable which is anxiety response after a stressor. And let's say you're operationalizing that as the state trait and anxiety inventory's state measure, so how much your sort of acute level of anxiety is following some sort of a stressor. Maybe you have like a prediction that people who have higher levels of resting heart rate are more stress reactive, so they'll report more anxiety once you've given them a stressor or something like that. Now, if you're enrolled in my class, I actually have a data set that's available on Blackboard. And if not, just do your best to kind of follow along with this example as I run through it. This is just a quick image of the data. You can see here we have 30 cases. For each person we have a resting heart rate at baseline in beats per minute and a score for the STAIS after the stressor. And I'm just putting this up here so that if you are not enrolled in my class, if you're just watching these videos on YouTube, pause the video and you could fairly quickly type these numbers into Excel or some other spreadsheeting or stats program, and you'd be able to work through the example with us, if you want. So okay, what we're trying to do here is test the model, and by that I mean test to see whether an augmented model that includes the predictor variable baseline heart rate to predict anxiety is a better fit for the data than a compact model which does not include that predictor variable, which instead just only predicts anxiety based on average level of anxiety for the sample. And so work through this in Excel or in SPSS and ask yourself, is this model significant? And explain what that means in plain English if you can. Also, what's the effect size for the relationship between baseline heart rate and post-stressor anxiety? And again, explain in plain English what that means, what that it means to say that there is a particular effect size. Also, try to interpret the model. Write out an equation for the model and interpret the coefficients. Think, how would I explain what these coefficients mean? B sub 0, B sub 1 for the augmented model. If I was trying to explain them to a friend or colleague, what would I tell him or her? And then see if you can apply the model and use the model to predict how much anxiety a person would have if they began at baseline with a resting heart rate of 85 beats per minute. So hopefully you didn't have too much trouble running through this little practice example. It's not really all that different from stuff we did in the last lecture, but it's always worth practicing to help yourself learn. Here's an interesting point that you might have thought of as you were going through the steps of your analyses. When it came to interpreting the regression coefficients, particularly the intercept B sub 0, does the intercept really make sense, or does it make sense to interpret the intercept the way we construct it in this model? What I mean is, normally we think of the intercept as being the value on the outcome variable that the model predicts when the value on the predictor variable is 0. In this case, our predictor variable is heart rate. Does it really make sense to try to predict the value of stress someone has if their heart rate is 0? Like, would we ever have someone in a study who has a heart rate 0? Or would we ever wonder about the anxiety for someone who has a heart rate of 0? Probably not. It doesn't mean that the model is wrong or that it's mathematically incorrect to compute a value for b sub 0. It just means it's a little bit difficult to interpret, practically speaking, what that value means or what it's good for. You might have the question, well, is there anything we can do to make b sub 0 more interpretable, more useful for us? And the answer is yes. As I mentioned in the previous lecture, there's a procedure called centering the predictor variable where we create a new score for each case, that is each person in our data set, by subtracting the mean for the predictor variable from that individual person's value on that predictor variable. So for each person in our data set, we take whatever his score or her score is for heart rate, our predictor variable, and subtract from that value the average for everyone's heart rates averaged together. This creates a new score that's called a mean deviation value. And then we run the analysis again. We repeat our regression, except this time, instead of using our regular uncentered predictor variable, we use our centered or mean deviation value for the predictor variable. Now, if you're trying to see how this would work in SPSS, it's really not all that hard. Here's the same data that I presented before in SPSS. Again, if you're enrolled in my class, you have access to this data set on Blackboard. If not, you could, using the information up a few slides back, you could just copy this information into SPSS, or you could pretty much do the same sort of steps in almost any other stats program. Anyway, what I'm doing first is I'm right-clicking on the column for my predictor variable, heart rate, and that just gives me a quick pull down where, among other things, I can get some descriptive statistics. So this is just kind of like a shortcut to get some simple descriptives on any variable. In this case, what I'm interested in, of course, is the mean. And it happens to be the case that the average resting heart rate or baseline heart rate for all the folks in my data set is 71.4 beats per minute. So I'm going to use this information to create my new variable, which is my centered or mean deviated value for the predictor variable. And in SPSS, one way to do that is to use the menu commands transform compute variable. That opens up my compute variable window here. I'm going to enter a name for my new variable. I'm just using CTR-HR to suggest that it's the centered heart rate. Heart rate being, again, my predictor variable. I'm clicking here on the label, or the type and label button, which just opens up this other little dialog box here, and I'm giving that variable a full label to sort of remind myself what it really is. In SPSS, variables can have a variable name. They can also have a longer label, which often contains more descriptive information about what the variable really is. So you can kind of see here I've typed in centered heart rate in beats per minute. I've also indicated that this variable is going to have a numeric type variable, not a string variable. I'm pretty sure that's the default, but I'm just making sure that's set up properly. You don't need to do that step. I'm hitting continue, and then in the field over sort of towards the right for the numeric expression, I'm entering the following numeric expression: heart rate minus that mean value, 71.4. So what this is going to do when I hit OK is it's going to go into my data set, create that new variable, CTR-HR, and for each person, they get a value on that variable that's equal to whatever their heart rate value is minus the mean for the entire sample, which happens to be 71.4. There are some other ways you can get the same calculation to work, but this is probably just the quickest way I could think of when I decided to set up this lecture. So now you can see kind of what this looks like here. We've got our same data set, except now there's this new variable, CTR-HR. I've right-clicked on that to open up that little pull-down menu and get some quick descriptive statistics. And obviously the mean for the mean deviated values, the centered values, will be 0 because of just the way the arithmetic works out. But notice that the standard deviation is the same for this variable as it was for our original predictor variable HR. if you don't believe me, just back up a couple slides and you'll see the transformation that we've done, or the calculation that we've done, has just shifted the mean of the distribution of values. It hasn't changed the shape of that distribution. It hasn't given us a new standard deviation or a new sort of shape. It hasn't made the distribution more or less skewed. It's just kind of slid the distribution to the side. And now I can go ahead and run the analysis again, run my regression again, except this time, instead of using regular heart rate, uncentered heart rate, I'm going to use centered heart rate, or mean deviated heart rate. Now, the output that I presented on this slide is the original ANOVA table and coefficients table in the sort of the upper portion, and then the new ANOVA table and coefficients table for my sort of reanalysis or my rerun. And you can see here that really the model is basically the same. So the value for the F statistic and the P value in the ANOVA table, that's the same. None of those sums of squares or mean squares change. And indeed, the slope in the coefficients, the value for B sub 1, that stays the same. The only thing that changes is the value of B sub 0. It was negative 49.46. Now it's positive 0.54. So here we have two scatter plots for our data. In the scatter plot on the left, you see the line that is the model for the data using the uncentered predictor variable. And on the right, you see the model that the line that's the model for the data using the centered predictor variable. And notice that in both scatter plots, the data is the same. And in both cases, the models are almost the same, or at least they have the same slope. What's different is their intercept, that is where the line of the model crosses the y-axis. And the reason it's different because this centering process, in a sense, slides the y-axis from 0 on the x-axis where it normally lives. That's sort of way off to the left in the leftmost scatter plot. It slides it to the right to a point on the x-axis that corresponds to the mean of the predictor variable. So if you recall, the mean of the predictor variable heart rate was something like 71.4. Notice that the y-axis now occurs at 71.4 on our x-axis. And as a consequence of that, the model, the line of the model, crosses the y-axis at that point, at the point which is the mean for our predictor variable. The consequence of this, or what this means, is when we run a regression and we use a centered predictor variable, the intercept is now the prediction that the model makes when the predictor variable is at its average, not when it's at 0, which is what it is for an uncentered predictor variable, but at its average. Put another way, this is the prediction the model makes for people with an average level of whatever our predictor variable is. And B sub 1, the slope, that's just the change in the outcome variable associated with a 1 unit change in the predictor variable, which is the same as what it was all along. That hasn't changed as a consequence of our centering. So centering a predictor variable can be useful in situations where that predictor variable doesn't have a naturally interpretable value of 0, like the case of heart rate. It's not normally very interesting to ask what the model predicts for someone who has a heart rate of 0, or if we had a predictor variable that was IQ. It's not, there are no people with 0 IQ. So sometimes in situations where our predictor variable doesn't have a natural 0 that's very meaningful, we like to center the predictor variable because it makes the intercept for a model that we make with that new centered value more interpretable. The intercept is now the prediction that the model makes when the predictor variable is at its average, which is almost always interesting as compared to when it's at 0, which sometimes is not interesting. Hopefully that makes sense. Now, there are at least one or maybe two other reasons why we sometimes like to center predictor variables, but I'll get to those in later lectures. For the time being, I'll just trust that you kind of understand what we've just covered, and if not, please rewind the video and watch it again. Assuming you're not doing that right now, let's move on and talk a little bit about regression diagnostics. Regression diagnostics is just a term given to a whole set of techniques that are used to evaluate the fit of a model to the data. And they're often used to detect problems with models where the model becomes biased, where it gives problematic predictions for the outcome variable. No, we call these regression diagnostics because of reasons that probably have to do with kind of the history and traditions of how textbooks are written. These seem to show up a lot more in textbooks on regression, but really they can be applied to any analysis that uses regression, including ANOVA. You can and you really should use this stuff when running, let's say, a factorial ANOVA, not just when running a multiple regression. Now, I said we often use regression diagnostics in situations where we're worried about bias, and probably that's a good enough reason to review what we mean by bias in the context of regressions and model comparisons and so on. Well, here what we're talking about is non-random over or underestimation of parameters. So our regression coefficients, our b sub 0, our b sub 1, b sub 2, and so on, can be systematically wrong. They can tend to undershoot or overshoot what the real values for those model coefficients are in the population. That is what the parameter big B sub 0 and big B sub 1 really are. What causes bias? Well, I've talked about this a little bit before, but bias can be caused by the presence of outliers or by violations of assumptions that we're making about the data that we're using to fit our model to. Now, often these two problems go together, and I hope I made that clear in previous lectures. Often addressing one can help address problems with the other. Particularly finding and dealing with outliers can often make concerns about violated assumptions much less, well, concerning. Now, with that in mind, let's look for some outliers. How are we going to do that? Well, there are some different options, and the first two that I can think of is we can do some graphing, and we can look at standardized values for our variables. Now let's start with some graphing. Now if you're working in SPSS, you can use the graphing functions to create histograms for your two different variables. You can also get some of those same output from the Explore module in descriptive statistics. So if you go to Analyze Descriptive Statistics Explore, you get this nice module which gives you some different tools which you can use to, as the name suggests, explore your data. I'm going to go ahead and take heart rate and anxiety and put them over into the box called dependent list. They're the two variables I'm looking at. I'm going to click on the button for statistics and ask for descriptives, put a little check there. I'm also going to ask for outliers, which are going to give me the highest and lowest values for each of those two variables. Go ahead and hit continue. Then I'm going to click the button for plots, and I'm going to ask for histograms. I guess if you want, you can ask for box plots. I'm also going to ask for normality plots with tests. Hit continue, and then go ahead and hit OK. So you get a fair bit of output from the Explore module. Here are just a couple pieces, two histograms that I get when I run those steps in that module. If I was working in the output area of SPSS, I could double click on either of these to open up the chart editor and superimpose a normal curve on them, just to kind of get a sense of how normal or non-normal they are in appearance. Graphing like this doesn't suggest any really obvious outliers, but the sample size is kind of small. We're 30 people. We're kind of on the margin between what we consider a small sample and a large sample. The distributions are sort of non-normal in shape, so it's kind of hard to be really sure if there are outliers there. And by the way, you might be wondering, is it bad that our sample distributions are not normal for these two variables? Not really. Normal sample distributions are often nice, especially if we're studying variables that we think ought to be normally distributed. Like, I'm not a cardiophysiologist, but it wouldn't surprise me if in a sufficiently large sample we'd see heart rate values for the heart rate variable that are kind of normal in shape. And I'm sure that if we had a large enough sample, we'd see levels of anxiety that kind of follow a normal distribution. We've got a relatively small sample here, so it doesn't totally surprise me that we don't see that nice bell-shaped curve. Again, sample distributions that are normal are nice, especially if we sort of expect them to be normal, especially if we have larger samples, but they're not absolutely necessary. A lot of the calculations we're going to make, calculations of means, calculations of test statistics, and so on, are going to work just fine, or at least the sampling distributions are going to be very usable if we have large samples. And our sample here is about 30 people. I don't know, it's sort of in the range of being a large sample, so we're probably not too awful bothered by it. Anyway, let's go back to looking for outliers after briefly digressing on the normality or non-normality of sample data. So graphing is one option for looking for outliers. Another option is to compute standardized values for our variables, in this case our outcome variable and our one predictor variable. If we compute standardized values, if we compute z-scores for these variables, then we should see, we would expect to see relatively few large values, large standardized values, so large positive or large in the negative direction values. For instance, we shouldn't see an awful lot of cases that have standardized values of our predictor variable that are greater than 2. Now, if our sample distributions are normal, and remember, they don't absolutely have to be, then we can use some simple guidelines. If we have a normal or more or less normally distributed set of data, then we would expect a maximum of about 5% of the cases to have standardized values that are greater than 2 or less than -2. And we expect around a maximum of 1% of the cases to have standardized values that are greater than 2.5 or less than -2.5. And really no, or very, very few cases should have standardized values greater than 3 or less than -3. Now, there are different ways to get standardized values in SPSS. You could compute them using the compute module. You could, as I'm showing on the screen here, you could go to Analyze Descriptive Statistics, Descriptives, select the variables you want, in this case heart rate and anxiety, and then click the little box that says Save Standardized Values of these variables. Once you do that, you kind of can't see it here because it's obscured in the background, you get new variables added to your data set that are standardized versions of heart rate and standardized version of STAIS, our heart rate and our anxiety variable. Then, if you go to Analyze Descriptive Statistics Explorer, you can just ask for descriptive statistics of these new z-score values. You can see I've clicked them over into the dependent list. The z-scored values or standardized values for heart rate, the z-scored values or standardized values for anxiety, and I've clicked on the statistics button to ask for outliers. So looking then at the output that I get from my Explore analysis, you can see my highest and lowest values, or I should say my highest and lowest standardized values for heart rate and for anxiety. And these standardized values don't suggest any obvious outliers either. So I'm not seeing any values that are in the range of +3 or -3. I don't see, I think, any values even in the range of +2.5 or -2.5. There's one value on standardized heart rate that has a value of -0.2, and that person is 2 standard deviations below the mean on his or her heart rate, but that's not impossible. We just shouldn't see a lot of those extreme values, and in this data set we don't. So what causes bias in estimation? Well, one cause can be outliers, and as we saw here with some really quick graphing and some quick eyeballing of standardized values, there's not a lot of evidence for outliers here. So bias can be caused by the presence of outliers in our data set. It can also be caused by violations of assumptions that we're making about the data for the particular types of analyses that we're doing. It's always worth considering the various assumptions that your analyses make. And for the time being, I'm going to focus on assumptions of normality, but from the perspective of the normality of the residuals or the errors that our model is making. Now, how am I going to do that? Well, I'm going to look at some graphs, I'm going to look at some standardized values for those residuals, and I'm even going to do some formal tests of the distributions of those residuals. Now I know this slide looks really fussy and complicated, but it's really not that bad. All I'm doing here is just running the regression again and asking for a few additional options. So I'm going to analyze regression linear. My dependent or outcome variable is anxiety. My independent or predictor variable is centered heart rate. And before clicking OK, I'm clicking the button that says Save. That's allowing me to save values for new variables into my data set. And I'm clicking here, or I've checked the checkboxes here for unstandardized and standardized residuals. I also meant to click the box for studentized residuals, but I accidentally clicked the box for studentized deleted residuals. And I don't think I'm going to talk about those in this lecture, at least not yet. So I think what I meant to do is click the box for studentized residuals. So if you're doing this on your laptop or on your computer, click the boxes for unstandardized, standardized, and studentized residuals. Don't click the box, or at least you don't have to click the box for studentized deleted residuals. I'll talk about those in a different lecture. Anyway, once you've clicked all those boxes, hit continue, and then in the main kind of work area of the module, hit OK. So you'll get your regular regression output, but for the moment don't look at that too closely. Just go back and look at your data set, and you can see here we've got values for the residual, that's res_1, that run up and down here. We've got values for the standardized residual, that's zre_1, and then we have values for the standard studentized deleted residuals. Again, that was a mistake. It really should just be the studentized residuals. But the point is, I've gone ahead and sorted the data. If you right click on the column, you can sort ascending or descending. I've sorted descending on the standardized residual, just to illustrate that there are a couple values, a couple cases that have large absolute values of the standardized residuals. So a few cases that have rather large residuals that are, the model misses quite a bit. Somewhere in your regression output, you should probably also have a table for residual statistics, and here you can see minimum and maximum values for various residual statistics. So if we look here at the standardized residual, we can see that one case has a value of -2.3, another has a value of 2.25. For studentized residuals, there's one that has a value of -2.4 and one that has a value of +2.4. There are a couple of cases with large absolute values of these standardized residuals. Well, how many is too many? Again, assuming that our errors, our residuals, are normally distributed, and this is an assumption we make for our analyses, we shouldn't see that many cases with large absolute values for these standardized or studentized residuals. So we shouldn't see more than about 5% of our cases having standardized values for residuals greater than 2 or less than -2. Or even fewer cases greater than 2.5 or less than -2.5, and really no or very, very few cases that are greater than 3 or less than -3. In this case, we see a couple, but we don't see an awful lot. If we saw an awful lot, if we saw values, if we saw cases that have, in a sense, outlying values on their residuals, we might really worry that there's some sort of problem of bias, potentially, where our model is really over-predicting or really under-predicting certain types of folks or certain types of cases in our data set. By the way, you might be wondering, because I've mentioned it a few times, what's the difference between a standardized and a studentized residual? Well, a standardized residual is just a residual, all the residuals divided by their standard deviation, just like any other standardized value. So you take a particular residual and you subtract it from the average of all the residuals, which is just always going to be 0, and you divide by the standard deviation of the residuals, and that's a standardized, or like a z-score for a residual for a particular case. Studentized residuals are very similar. They're just residuals divided by an estimate of their standard deviation, and that estimate varies from case to case. So it's not like the one standard deviation of all the residuals, it's an estimated standard deviation that is allowed to kind of vary somewhat. This usually provides a more precise estimate of error variance for each case, but basically it works the same way that a standardized residual does. That is, we can apply the same basic guidelines when looking for extreme values. So I often ask for both standardized and studentized, but I often kind of treat them the same way. Maybe that reflects a little bit of sloppiness on my part, but hey, that's just me. I gotta save brain bandwidth somehow. So in our data set, if you're looking really closely, I set up this data set particularly to have two cases, case number 10 and participant ID number 10 and participant ID number 16, that have fairly large values for their residuals. These are values which are not ridiculously large, but are large enough that you might want to look into that a little more closely. You might ask, well, gosh, why does the model do relatively poorly in predicting or describing the data on the outcome variable for these two cases? How we can explore that, well, we could try to make some graphs, and we could try to highlight who those outlying cases are. So perhaps the first thing you could do is just go ahead and make a regular scatter plot, as I have done here. We've got obviously our predictor variable heart rate and our outcome variable anxiety. By the way, it doesn't really matter for the purpose of regression diagnostics, at least at this point, whether we use our centered or our uncentered predictor variable. And here, if you've done this in SPSS, you can go into the output and find the scatter plot. You can double click on it to open up the chart editor, and using a little bullseye tool that you'll find in the toolbar, you can bullseye different cases. Here I've obviously bullseyed the two cases that are kind of the most extreme in terms of their residuals. They're the ones that have the largest residuals, and when you bullseye them, you get the case number for that particular case. Now, case number just refers to the row in the data set in which that particular case occurs, and since I've sorted the case, was it ascending or descending? I've sorted all the cases on standardized residuals, so clearly the ones with the biggest residuals are going to occur at either end of that sort, case 1 and case 30. So again, that's what I've done here, just to kind of visualize where are these outliers, and by highlighting their case number, I guess I could track back to find their ID number and maybe even look up the raw data from the sessions that those two participants were in and find out, well, who are these people? So again, just note here that these ID number, or these numbers here you see, are case numbers, not ID numbers, again, because I sorted on the standardized residuals. Now, it's worth noting, in addition to just finding out who are these cases, it's worth noting whether or not all the extreme errors, that is, the cases with the largest residuals, all occur on one side of the model. Like, it would be weird and maybe bad, and at least worth investigating, if our extreme outliers occur in terms of the model overshooting cases, or if our extreme outliers occur in terms of the model undershooting cases. Now in this case, or in this example I should say, the model overshoots one extreme outlier and undershoots another, so maybe that's not quite so distressing, but you could imagine a situation in which your model just does really poorly for predicting certain types of cases, and particularly it does poorly in the sense of consistently overshooting them or undershooting them. You could definitely make note of that if you were kind of exploring the nature of your errors or the nature of your residuals for your model. Now, this doesn't seem to be happening here, so we can probably maybe move on a little bit. Oh, and I should say it would also be bad, or at least worth noting, if all of the extreme errors, that is all the largest residuals, occurred at one end of the predictor variable. For instance, if all those extreme residuals were kind of at the low end of heart rate or at the high end. I mean, that would kind of give you a sense that, gee, our model does pretty poorly among people who have high heart rate or among people who have low heart rate. That would be maybe a problem, at least something you'd want to think about a little bit before proceeding with your analyses and maybe your interpretation of your analyses. Now again, in this example, it kind of has to do with how I set up this fake data. It happens to be the case that the model has one extreme outlier, pardon me, at the low end of the predictor variable, that's case number 1, and one extreme outlier at the relatively high end of the predictor variable, that's case number 30. So again, not as much of a problem, but in principle that's something that you might want to notice if it is happening and investigate further. Now another trick you can do, which is kind of similar, is you can plot the standardized residuals against the standardized predicted values. It's just another way to highlight outliers. So you can generate in SPSS's dataset very easily the predicted values that the model makes for each case, and you can standardize them. Those are obviously just standardized predicted values. And you can also, of course, generate rather easily standardized residuals. And if you make a scatter plot of those, if you double click on the scatter plot in the output and open up the chart editor, you can again try to bullseye cases, kind of as I've done here. And you know, surprise, surprise, because this is fake data the way I set it up, it's the same two cases, case number 1 and case number 30, that are these kind of unusual outliers. You know, this is you know, suggesting that when we're predicting at kind of the low end of prediction, the model makes a pretty big error, and when we're predicting a relatively high end of prediction, the model makes another rather big error. So again, just to repeat that, or kind of you know, further that point, it would be bad if extreme errors all occurred at one end of the predicted values. Like if the model misses the most when it's predicting large values for the outcome variable, or it misses the most when it's predicting small values for the outcome variable. Now that doesn't seem to be happening here, but if it was, that would make us concerned about sort of bias in our model. Like our model does really well when it's predicting kind of in the low end of the outcome variable, when it's predicting modest, modest levels of stress in this example. But as it gets into the range of predicting high levels of stress, then the model just breaks down in the sense that its errors get much worse, much larger. Now, I made those scatter plots using just the chart editor, generating variables in the data set and then using the chart builder and chart editor, just because I tend to like working that way. It's probably a bit fussy. It's worth noting that the regression diagnostic graphs like I just made, and indeed many others, can be made very easily from within the regression module of SPSS. So if you're working through a regression, you're using analyze regression linear, you've set up your dependent, that is to say your outcome variable, and your independent, that is to say predictor variable, you'll note that there's a button in that module for plots, and I've clicked on it and opened up the little sort of ancillary dialog box there, and I can plot all sorts of different options. So I can plot standardized residuals against the outcome variable, or against the standardized prediction for the outcome variable, or so on and so on. I can even generate standardized residual plots and represent them as histograms and normal probability plots, that is PP plots. These are all kind of ways of exploring the distribution of the distribution of residuals, that is the distribution of errors that our model makes. And it is, again, to be important, or it is to be remembered or to be noted that we do make some pretty strong assumptions about the nature of the distribution of errors that our model makes. We'd like to see a rather normal, not skewed, not containing a lot of outliers distribution of errors with our model. If we don't see that, then we start to worry that there's some unusual data in our data set that we're using to fit our model, or that there's something kind of odd about the variables that we chose to make up our model, and there's maybe some problem with bias in estimation, and so on and so on. So however you do your graphing, at least in this this data that I've made up, it's pretty clear that case number 1 and case number 30 are unusual. They're unusual in the sense that they have large values for their residuals. The model, in a sense, doesn't work very well for them, at least not as well as it does for the other cases in our data set. Now those people are participant number 10 and participant number 16. If you look at them closely, you see that participant number 10 has a relatively low value for baseline heart rate and a relatively high value for her state anxiety. And case number, or ID number, participant number 16 has just the opposite problem. He or she has a relatively high value for heart rate and a relatively low value for anxiety. Now, the simple fact that these cases are outliers isn't alone a problem. I mean, we expect a certain small number of outliers in almost any distribution. However, they do merit some investigation. It's probably worth asking, why is it the case that these people are outliers? And recall that there could be at least two problems that could lead to outliers. One is that there are some sort of methodological or measurement problems. It might be the case that on the day that we ran participant number 10, the software on our psychophysiological apparatus was updating, or it wasn't working well, and thus the recording was compromised. Or it might be the case that on the day that we ran participant number 16, that was in the middle of the midterm period for the semester, and most of the students are really stressed out and anxious because of tests and papers and things like that that are due. This is part of the reason why I think it's really important to have a good laboratory notebook and train all your research assistants to record carefully what is going on the day that you run participants in your lab, or that you gather data from participants out in the community or wherever it is that you're doing your research, because there may be clues that will lead you to could lead you to diagnose or to recognize problems with measurement after the fact, or could provide a plausible explanation as to why there were problems that led to outliers or extreme outliers on your model's residuals. Another issue that's maybe a little bit more subtle is it may be the case that in sampling a particular population, you have accidentally sampled people who really aren't part of that population. They've kind of drifted in from some other population that you're not as interested in. In thinking of examples for this, I can't help but think back to my dissertation research. At the time, I was looking at the effect of alcohol intoxication on certain features of visual attention as operationalized with an eye tracker. I was looking at things like saccadic eye movement and how that was affected by intoxication. Now, my population of interest was sort of, generally speaking, people, or perhaps college population folks, people in their sort of late teens and early 20s, and I was sampling from that population, of course. And it was the case that at the end of data collection, and when I was looking at the data, I noticed that in many of my analyses there were these, I think it was like 2 or 3 particular cases who had really unusual values for their residuals, and the residuals worked out in such a way that it was the case that these particular individuals made very few eye movements on the task that I was giving them to do. This was a task where participants had to search for a target amidst a field of distractors, and most people, when they did that task, have to move their eyes around quite a bit, sort of, blinking and clicking, if you will, from one object to the other until they find the target. And that's true whether they're drunk or whether they are sober. These particular cases made very few, or in some cases no, eye movements on any of those trials, and that just struck me as really weird. And I noticed it once I noticed these big residuals that the model had for these different analyses I was doing. And so I went back and I looked at my laboratory notebook, and I couldn't really find any indication that the software was not working on the days that I recorded those participants, or that my lab procedures were any different. I ran all my participants myself, so I didn't even have any research assistants who might have made mistakes. Clearly I can make mistakes, but I checked my notes. I was pretty confident that there wasn't a methods or measurement issue going on there. And then I actually went back and looked at some of the notes I'd made when interviewing these participants, just chatting with them as they were sobering up in my laboratory, and I noticed that all of these participants were all semi-professional athletes. They were people who were either college athletes, or in one case someone who had played on a minor league baseball team and had come back to college afterwards. And I thought to myself, maybe this makes sense that these people don't move their eyes as much as quote-unquote regular folks do when doing a task like the one I'd given them. Someone who's trained as a pitcher in a baseball team, or someone who's trained as a goalie in a soccer team, which are just 2 of the examples, are folks who probably are really good at scanning a field, literally a sports field, and looking for a stimulus, like a ball, like looking for the batter, looking for the incoming soccer ball into the goal. And they may, after years of doing this, be just better able to find the target, whatever that target is, the simple sort of geometric shape in my task, without moving their eyes very much. In a sense, I wondered, maybe they're not really part of the population I'm studying. They're obviously college students, and they're obviously regular people, but in a sense they're different than most of the regular people in my study. And I thought about this a little bit. Am I justified in saying that because they're part of a different population, not the population I'm expressly studying, I'm not expressly studying athletes, am I justified in saying that they don't really belong in my data set? It's a little bit of a tough call. And the point I'm making is sometimes it's the case that maybe our cases, sometimes it is the fact or is the possibility that the cases that have these unusual outliers in terms of the residuals shouldn't really be part of the sample that we're studying because they've really wandered in, so to speak, from another population. Now, let's assume that we have some good reason for getting rid of, in this example, ID number 10 and ID number 16. Let's imagine we checked through our notes and we found, oh, there were some terrible methodological problems on the days that we recorded those participants. Or we checked through our lab notes and we say, oh, we're studying anxiety, or heart rate and anxiety, and these people are folks who were accidentally referred into our study from the cardiophysiology unit at the local hospital. So they're people who have heart problems. And although it's worth studying folks with heart problems, they are not really part of the population of normal, unaffected adults who we really mean to study. Whatever. It's just a silly example, but let's assume we have some pretty good reason for thinking these folks ought not to be in our sample because they're not really part of our population, or we have some sort of methodological problems that damaged or distorted their data. In SPSS, we have a lot of options for what to do with cases like this. We could, of course, just go into the data set and delete them. Although I tend to discourage that because once you delete data from your data set, it's gone forever. And so that's not so great. One thing I would tend to encourage you to do instead is take advantage of the select cases function that SPSS has. So if you go to data, select cases, and then if you click on the radio button for if condition satisfied, you can set up a logical condition that will filter cases. So in this case, I say select cases if ID number does not equal 10 and ID number does not equal 16. So what SPSS is going to do is select all the cases that are not ID number 10 or ID number 16, and it's going to filter those cases. And you can see here those in terms of the little box at the bottom. I've clicked the radio button for filter out unselected cases. So unselected cases, that is case number 10, ID number 10, ID number 16, they're filtered, they're removed from analyses. We could also copy them to a separate data set, or we can even delete them if we wanted, kind of like just by hand deleting them from the data set. I'm just going to filter them. And if you do this in SPSS, you'll notice that a little hash mark passes now through the case number margin on the left side of the screen for the case that corresponds to ID number 10 and the case that corresponds to ID number 16. Those people still exist in your data set, but for the purposes of subsequent analyses, they will not be included. If you go ahead and run your regression again, now having filtered the case, those two cases, you'll see some interesting changes in your analyses. So right here, I've got on the top margin, the ANOVA for the model when those two cases are included, and then on the bottom, the ANOVA for the model where the cases are removed. And you can see the value for the F statistic goes up quite a bit, and correspondingly the value for the significance level or the probability goes down quite a bit. So removing those two cases or filtering them temporarily improves the model with respect to its test statistic. You can also see it changes the slope of the line of the model. So it also changes, or I should say it reveals a stronger relationship between our predictor variable and our outcome variable when we remove those two cases. If you go and make another scatter plot, the scatter plot will now not include those two cases, and if you look really closely, you'll see that the line is kind of a bit of a better fit to the remaining data, and also you'll notice that the value for R squared is a little bit higher. In fact, it's more than a little bit higher. Before, with ID number 10 and ID number 16 in the data set, the R squared was about 0.17. Now it's 0.43 or maybe even 0.44. So quite a better fit for the data once we've removed those cases. See, here's what it looked like with the data not filtered. You can kind of eyeball the line and it seems to be a little bit less fit into the data, and if you look at R squared value, R squared is smaller. So this may sound good. You could imagine running a regression, doing some regression diagnostics. In this case, we've really focused on outliers, and I should say focus on outliers in terms of residuals. And you can imagine saying, oh, let's get rid of these cases with these bad or extreme values in terms of the residuals, and we'll improve the fit of our model. Our R-squared will go up, our F value will go up, our P value will go down. This sounds fantastic. But caution, be careful about removing cases from your data set. It can be easy to convince yourself to do it. It can be easy to say, yeah, I'm pretty sure that the day we ran that one case, wasn't that the day that everyone in the lab was kind of distracted, so maybe we made some mistakes when we set up the equipment, or maybe that person was, maybe he's not a typical student in our college population, maybe I really shouldn't be in the population, so we can remove him. It can be easy to kind of talk yourself into cherry picking your data, which makes the data fit the model, when technically speaking, what we're really trying to do is make the model fit the data. The data is what it is. Our job as data analysts is to fit a model to it. Our job as data analysts isn't to make a model and then remove data until the model looks like it is just awesome and fits the data. The reward of cherry picking, at least the temporary or short-term reward, is apparent improvement in fit. You can kind of say like, wow, by getting rid of those two cases, our model now explains 44% of the variance in the outcome variable. That's great. We're awesome data analysts. But the risk is the model now fits the sample really well, but maybe doesn't fit the population really well. So you've created, by cherry picking, a kind of an artificial sample, a hyper-selected sample for which the model really fits. But if you were to try to apply that model to another sample from the same population, you would see either problems with estimation, bias in estimation, or even just a failure to replicate the basic findings. It's like, gosh, when we drew a new sample from the population, ran the model in it, R-squared was minuscule. How did this happen? Well, it's because whether you realized it or not, you fit the data to the model and not the model to the data. Caution again, or further caution, you should have good reasons to remove cases from your data set. For instance, the case is part of a different population, not the one that you're really trying to sample and develop a model in. Or there was some sort of problem with your data recording, the measurement didn't work properly, or the participants didn't behave properly, or there were problems with data entry. The research assistant who did data entry for that portion of the data set was careless, and you know this because you had to discipline him because you noticed he was texting on his phone instead of paying attention to how he was recording the data, or something like that. In this particular case, let's assume we have some good reasons to remove those data points. Again, maybe we have laboratory notes that tell us that there were problems with the equipment on that days. If that's true, then it makes sense to remove those cases. I'm not against removing cases from a data set. I'm just trying to argue that you should have a really good reason for it. And assuming you do, and this is obviously just a kind of a fictitious example, run the regression again, look at the new distribution of residuals, create some graphs for that, run some formal tests. I've gone ahead and done this right now. If this was in class, we'd spend a little bit more time doing this together. And at least as compared to the graphs of the distribution of residuals before, these graphs look a little bit more normal in shape. The histograms are obviously a little bit incomplete looking, but if you look at those QQ plots, which for our purposes are essentially the same as PP plots, most of the values of the observed data fall on the diagonal, which describes the predicted values that we'd see in perfectly normally distributed data. Moving on, I've just done a couple formal tests of the distribution of residuals, and you can see for the Kolmogorov-Smirnov test and the Shapiro-Wilks test, neither of them suggest a deviation from normality. All the p-values are greater than 0.05. But remember here, these tests tend to be rather underpowered in small samples. This sample's fairly small. So the simple fact that these tests are non-significant in and of itself isn't, entirely doesn't entirely settle the issue of whether the distributions are normal in shape. I've also gone ahead and got values for the skewness and kurtosis for the standardized residuals, as well as their standard error for their skewness and kurtosis. And I've done the math here to do z-tests on those values, and those z values for z are all really pretty small, and I know they're not going to be statistically significant. So again, looking at the new data set, the data set that's been filtered, we see a pattern in residuals which is more consistent with what we'd expect, which is that the residuals are more or less normally distributed. They don't appear to be extreme outliers. I didn't show that on this screen, but believe me, I looked and they're not there. And that's good. We've used some basic regression diagnostics to suss out how well our model fits the data, and we've identified a couple problematic cases and we got rid of them, and it looks like the model fits the data a little bit better now. Assuming we had good reasons to get rid of those cases, we should feel pretty proud of ourselves. Well, I hope you feel proud of yourself for paying attention to this lecture. I know these things are long. We're clocking in at about an hour here, as usual. What will we cover next time? Well, next time I'll do a little bit more about regression diagnostics, and I'll also introduce multiple regression. That's regression where there's two or more predictor variables, which is, of course, rather common in the realm of applied statistics in psychology and other behavioral sciences, and opens up some really new, kind of interesting avenues for exploration. So I'm really looking forward to that lecture. I hope you are too. Or at least I hope you're willing to stick around and watch it. You've probably got more important things or more exciting things to do in your life, but hopefully watching these videos is helpful for you. Anyway, that's all for today. Thank you so much for your attention. As I always say, I really do appreciate it. If you're enrolled in my class, please be sure to ask me questions if you have them. If you're not enrolled in my class, if you're just watching these videos on YouTube, then thanks. And also leave questions or comments in the comment field. I try and check those every few days, and if I see questions or comments, I try to respond to them. So thanks, and I'll see you next time. Bye-bye.